Yeah. So we'll go over the guess the number problem now. I kind of explained the solution, but I started recording after I explained the solution. So you guys can see my screen, right?
Yeah.
Yes.
Yeah. So this is the guess the number problem, and this is what the solution will look like. So this is what the binary search looks like. Basically, we have a variable to start at that sets our lower bound, that's called low. And then we have our upper bound, which is high. And in this problem, when our program is supposed to make a guess, and then they'll tell us if it's low, their actual number is lower, higher, or correct. So that's why I have a string over here to read in what they told us. And I'm basically going to say while the string is not correct, then the middle number is going to be equal to low plus high divided by 2. So in the case of 1 and 1,000, that would be 500 because 500 is in the middle. So that's what mid is equal to. And then our program is going to guess that. This line of code over here prints it out. I know it's not in Java, but I'll explain what it does. So this line 57 just prints out our guess, which is going to be the number that's in the middle of low and high. And then we read in the string that they give us. If they told us, well, no, my number is actually higher, we're going to have to shift our range over from 1 to 1,000 to 500 to 1,000 because they told us their number was bigger than 500. So to shift it over, we're going to take our low variable, which was initially 1, and we're going to make it 501. Does everybody get that? But we just shifted it from 1 to 501. So now we're searching in 501 to 1,000. Otherwise, if they told us it was lower, we're going to decrease our upper variable. Cool? Yeah, that's the solution to guess the numbers. Guess the number. And the next one I'll go over is musical scales. Was there anybody in the contest who was able to solve this problem?
Yes.
Okay.
Did you like my solution?
Yeah, it was very nice. Okay, so I'll give you some time to read a musical scales problem, and then I'll go over the solution for that. Also, is the fan noise very noisy for my computer?
I don't hear it.
Okay, good. Okay, so I'll continue with this problem. So in the musical scales problem, you're given a song as input. And for those of you who have ever played a musical instrument or been in choir, you know that there's 12 different notes. There's A sharp, B, C sharp, D sharp, E, F sharp, G, and G sharp. So in this problem, you're given a song consisting of any of these 12 notes. And there's also something called scales. So scales start at a note, like this is an example of the A sharp major scale. It has the notes A sharp in it, then C, then D sharp, then F, then G, then A sharp. Again, you can see that it repeats. And in this problem, you basically had to find which scales contained all the notes for that song. So for example, and if you look at this song over here in the sample input 1, there are 3 different notes. There's a C, there's D, and there's F. And the output is A sharp, C, D sharp, and F, because these are the scales that contain those notes. So if you look at A sharp over here, which they gave us a scale for, you can see that A sharp contains C, it contains D, it contains F. And that's why it's part of the answer. The C major scale contains C, it contains D, it contains E, and it contains F. So that's why it was also part of the solution. So that's what the problem was. And then for this case over here, the song consisted of the notes A, B, F sharp, G sharp, and C. But there is no single scale that contains all of those notes. So that's why you had to output none. Does everybody understand the problem? So once you understood the problem and what it was asking for you, the question kind of became, how do I code this? And if you remember, like a couple of weeks ago, we covered sets, maps, and lists. It's fine if you don't, and if you weren't there for that meeting. Basically, what a set does is it only stores unique values. So the idea for this problem is they can give us 100 C's, but that doesn't really matter. All we want to know is that there was one C in the song, so we can look for scales that contain C's. So that's why we'd use a hash set in Java to store these musical notes. And that way we only care about the unique notes. So in this case, it would be C, F. Over here, it'd be A, B, F sharp, G sharp, and C. And once we have that hash set containing these notes, the next question we have to ask is what's the best way to tell what notes are in a scale? Because you can see here a scale contains 7 notes and there's 12 different scales. So if you hard coded all 12 scales, that would be like 84 notes. Um, and that's a pretty lengthy process to do for this problem. But there are two key things to note. One of them is that scales follow a particular pattern. And you can see it over here. They actually told us what that pattern is. They say that a scale is defined by a note, like A sharp over here, and all other notes follow that in an arithmetic progression. So you can see the first note is A sharp, and then there's a step that's called a tone. So for a tone, you'd basically jump forward 2 notes. So for the A sharp major scale, you start at A sharp. There's a tone, so you jump forward 2 steps. There's a tone, so you jump forward 2 steps again. So far we have A sharp, C, and D. Now there's a semitone, which means you jump 1 step, D sharp. That's a D sharp right there. There's a tone, you jump forward 2 steps, F, 2 steps again, G, 2 steps again. And because this is music, it wraps around. After 2 steps after G is A, and then there's a semitone again, which is A sharp, and it repeats. So this is the pattern for a scale. And the reason this is useful is because instead of thinking of the notes as strings, as like literal strings, you can assign each of them a number. So you can assign the A as 0, A sharp a 1, B a 2, C a 3, all the way up to G sharp, which would get 11, I think. You would get 11. And this is useful because instead of saying what is 2 steps after A sharp, instead of saying like what's 2 steps after A sharp, we can just say what's 2 plus 0, because the A is 0. We want to jump forward 2 steps and to the B. So in that manner, we assign each of these notes a number. That way it's easier to work with. Because now what we can do with this pattern over here is a tone is just 2 steps, a semitone is 1 step. So we could store this pattern into an array that would look like 2, 2, 1, 2, 2, 2, 1. And what we would do is if I want to know what notes are in the A major scale, I would start at A, which is 0. I would add 2. I would add 2 again. I would add 1. I would add 2. I would add 2. I would add 2, and I'd add 1. And that gives me all the notes that are in the scale. So does everybody understand that idea of storing this as a pattern? That way we can easily find out what notes are in the scale. So I'll show my code for it. It's in C++, but I'll also explain what it does. So over here, an unordered set is the same thing as a hash set. And like I said, a hash set only stores unique values. We're only interested in knowing what are the unique notes in the song. We don't care that there are like 100 Cs. We don't want to check each of those Cs. We only want to check the C ones. And then I have a map. And for those who don't know what a map is, you basically give it a key and it will give you a value associated with that key. So over here, we're giving it a bunch of strings like A sharp, B, C, and so on. And then we assign each of those strings a number. So you can see over here from 0 to 11. Over here, we read in our input. And instead of storing it like C, D, F, D, we store the number version of those. So that's what U contains. It's a set variable. It contains the number form of these notes over here. Here's our pattern variable, which I was talking about, the tone, tone, semitone thing. Bool found any is whether we've found any scales. For example, in sample input 2, you can see there's no answer. So that's why we have found any to check whether or not we found anything. And if we did not find anything, then we print out none, like over here. Otherwise, we sort our strings because they want it sorted, and we print out our answer. And now for the actual logic. So over here, we basically go through every single note in our hash map. That's what this for loop is for. And then I have my start variable, which is equal to the number version of the scale I'm at. So for example, if the scale I'm currently testing, like let's say I want to check whether A major contains all of these notes over here. So that's what I'm doing over here. And the start variable is equal to 0 because A has a value of 0. So now what I'm doing is I'm going through every single number in this pattern and I'm adding that number to it. So you can see over here start equals start plus I. And I'm taking it mod 12 because if you ever looked at a piano, you know that after G, I mean after G, the note after G is A. It wraps around. So that's why I'm using the modulo operator over here. And this basically goes through every single note in the song. So C, D, F, A, B, F sharp, G sharp, C. And it checks whether all of those notes are inside the scale. And that's what the scale variable is over here. If it does not find something in the scale, that means this scale doesn't work. So we set good equal to false. And then outside of the loop, only if that scale works, do we set found any to true and we add that scale to our answer. So don't worry too much about the code, but as long as you understood the steps to solve the problem, that's good. Are there any questions about it? Yeah, so that's the solution to the musical scales problem. The next one is this greedily increasing subsequence problem. You guys can go ahead and read that. I'll give you like a minute. Okay. So in this problem, you're given an array of numbers and they want you to calculate something called a greedily increasing subsequence for that array. The first number of this GIS, that's what they call it. The first number of that GIS is always going to be the first number of the array. So and then the GIS of a position, the GIS of a position is going to have to be greater than the GIS for the previous position. So for example, G of 2 has to be greater than G of 1, G of 3 has to be greater than G of 2, and so on. That's why it's called greedily increasing subsequence, because each of these G's has to increase. And you can't randomly choose numbers to be part of that greedily increasing subsequence. The way it works is you have to start at the left side of your array and work your way rightwards to find the largest number greater than your previous one. So here we'll look at an example and this will probably be more clear. So as I said, they told us that the first number of the GIS will always be the first number of the array. So this is the array they gave us as input, and that's why 2 is part of the output. They want us to output the GIS, that greedily increasing subsequence. So we output 2. And now we want our second number, we want G of 2 to be greater than G of 1. G of 1 is a 2. So we start at the left of our array and we want to find the first number greater than 2. So is 2 greater than 2? It's not. Is 3 greater than 2?
Yes.
Yes, 3 is greater than 2. So that's why G of 2 equals 3. So we add 3 to our subsequence. Now we're on to the third position for G. We want G of 3 to be greater than 3. So we once again go to the array. The first number that's greater than 3 is 5. Even though there are 7s and 6s, the 5 comes first because we're starting on the left side. So that's why G of 3 is 5. Now we want G of 4. G of 4 has to be greater than G of 3. G of 3 was 5. So we start from the left. We want to find the first number bigger than 5. Even though there's a 6 over here, 7 is the first number from the left that is greater than 5. We add the 7 to our GIS. And now for g of 5, we want it to be greater than g of 4. G of 4 was 7. So we start over here at the left, we go right, and we try to see if there's any numbers greater than 7. Turns out there are not. 7's the greatest number. So that's it, we're done. And that's why the answer is 42357. I'll go through these two cases a little quicker. So we're here once again. Our first number will always be the first number in the list. So that's why it's 1. Now we want to find the first number from the left greater than 1. We look at 1. 1 is not greater than 1, but 2 is greater than 1. So our second number is 2. Now we want to find a number greater than 2. The first one we come across is 3. And we keep on going and we get 4, 5. In this example here, once again, the first number in the GIS is always the first number in the array, so it's 5. And now we want to look for a number that's greater than 5, but there isn't such a number, so 5 is our only answer, and we just print that out. Okay, yeah, and number on the top, somebody asked a good question, like what this number in the top is. That's how long the GIS is. So over here, the GIS has a length of 4, the GIS has a length of 5, and the GIS has a length of 1. So that's what this number in the top is over here. And did anybody solve this in the competition?
My team did.
Nice. Okay, so I'll go over the solution for this problem. So initially it may seem confusing, like
Ms. Horton was confused why you have to start at the beginning of the array each time.
We have to start at the beginning each time because that's what they told us to do. They want us to find the leftmost integer in A that is strictly greater than g of I minus 1. So I was just kind of describing the process. The actual answer doesn't need you to go like start from the left and go rightwards each time, but that's what
That
they
makes
kind of
sense.
want. Yeah.
That's fine.
So when you think about the problem, like that was a good question because the problem's telling you that for each g of I, you have to start on the left and then go right and start on the left and go right. But when you think about it a bit, when you think about this problem a bit, you realize that all it comes down to is that you realize that there's a pattern over here. What do you guys see about 2, 3, 5, 7 and this array over here? Does anybody see any pattern? The pattern is our answer is pretty much choosing the closest biggest number. So for example, we choose 2, the next biggest number is 3, the next number that's bigger than 3 is 5, the next number that's bigger than 5 is 7, and that's it. Same thing over here. We choose 1, we want the next biggest number, that's 2, the next biggest is 3, the next biggest is 4, the next biggest is 5. And that's actually the solution for the problem. You just choose a bigger number each time, the first biggest number you come across. So that's why it's 2, 3, 5, 7. And over here it's 1, 2, 3, 4, 5. So to actually code this, you would have a variable to keep track of what the first number is. And each time you come across a number that's bigger, you update that number to this new bigger number, that 3 is bigger than 2. So we update our variable to 3. And then we also add 3 to our answer. So here's what the code looks like. And you can see it's fairly short compared to other stuff. Don't worry about this stuff. It's just like the input, that kind of thing. GIS is our list. It's our list that contains our answer. So the first thing we add is array of 0. R is the array over here that they gave us, like 2, 3, 1, 5, 4, 7, 6. That's what that is. And the first number is always in our answer. We also have this variable called first. I probably should have renamed it to like biggest so far. I'll do that right now, so it's easier to understand. And this biggest so far variable, it contains the biggest number that we found so far. And initially that's just the first number. That's why we set it to array of 0. Then what we do is we go from index 1 to the end of the array, and we check if this position in the array, so if array of I is greater than the biggest so far. So for example, in the case over here, 3 is bigger than 2. We're going to update biggest so far to that number. So we're going to change biggest so far from 2 to 3 because 3 is bigger than 2. And we're also going to add that number to our answer. So that we add 3 to our answer. So then if we continue through the array, biggest so far right now is 3. We look at 1, is 1 greater than 3? No, it's not. We look at 5, 5 is greater than 3. So we add 5 to our answer. And now we change biggest so far from 3. We change that into 5. And then you just go through the rest of the array, you do this, and then you print out the size of your list, gis.size, and this just prints out each number in the list. Are there any questions about that?
What did you type def the VI to? Is that vector int?
Yeah, type def, yeah, it's vector int, yeah.
Okay.
And PB is pushback. Okay, I'll go over the air conditioned minions problem after I give you guys a minute to read it. I think you only really need to read the bottom 2 paragraphs from like you're planning to construct several rooms in your new hideout. I don't think the first two paragraphs are necessary. Okay. So basically in this problem, you have a bunch of minions who are working for you and they have optimal temperature ranges in which they work really well. And you have you want to know how many rooms. You can basically set the temperature of a room to any number you want, but you want to find out the minimum number of rooms you need for these minions to work in because they have different optimal temperatures. So for example, we have 3 minions over here, and the first minion can work well if the temperature is like 1 degree or between 1 to 2 degrees. The second minion can work well if the temperature is in between 2 to 4 degrees. And the third minion can work well if the temperature is in between 5 to 6 degrees. And the answer is 2 because the optimal solution would be to have one room where the temperature is 2 degrees and you put these 2 minions in there. And then you have a second room where the temperature is like 5 or 6. It doesn't matter because this guy will be there on his own. So for this one over here, the solution would be to have a room with temperature 2 for this first person. Then you would have a room with temperature 5 that would work for both of these minions because they have ranges from 3 to 5 and 4 to 6, and 5 is in both of them. And then for this minion, these 2 minions over here, you could have a temperature of 9. Does everybody understand the problem? And that's a total of 3 rooms. So if we draw this out, okay, if we draw this out, so we have the first minion's optimal room temperature from 1 to 2. We have the second guy, what is it, from 2 to 4. And then we have the third person from 5 to 6. So you can see that the optimal number of rooms is the minimum number of lines you need to intersect these these horizontal lines. By the way, the horizontal lines represent the temperature. So this is like 1, that's 2. That's, wait, I drew that wrong. Okay. Yeah, that's what it should look like. That's 1, that's 2, that's 4, that's 5, and that's 6. And the answer for this problem is the minimum number of lines you need to intersect the horizontal lines. So these horizontal lines represent the temperature ranges for the minions. And the horizontal lines represent the temperature you want to set each room to. So over here, we just need 2 rooms. We could set it to temperature 2, and over here, like 5. It doesn't matter too much. In the third example, it would be this. The lines would look like 1, 2, and then it would be 3, 5, 4, 6 is like that. 7, 9 is like that, and 8, 10. And this is just a visual to help you guys understand the problem better and how it works. So over here we have, this is for test case 2, we have these 5 minions with these temperature ranges. With these 5 temperature ranges. And then for the rooms, we could have temperatures like that. This could be 9, this could be 7 or something, or 6, 5, and that could be 2. So first, to code this, if you're coding this in Java, you would need a pair class. And the reason you would need an object class is because each minion has 2 pieces of information, their lower bound for the temperature and their upper bound for the temperature. And Java doesn't have a pair class to do that, so you'd have to code your own. But C++ has one. It's called pair. Wherever you see PII, that means it's a pair of 2 ints. And P.fi means that it's the lower temperature that the minion likes, and P.se means it's the upper temperature that the minion likes. And the idea for this problem is you want to sort these minions by the upper temperature. You want to sort them by their upper temperature. So let's just pretend they'd given the input to us in a random order. In order to process these minions efficiently, we'd want to put them in an order. Oh, I disconnected this. We'd want to put them in an order where we sort them by their upper temperature. And the reason for this is because, let's say for this first minion, you want to set the temperature for his room to this very upper temperature. That way he's more compatible with people who have higher temperature preferences. So you set it really high, and in this case, it doesn't, this guy's on his own. This is not a good example. But in the case of this minion over here, the idea is you would have to set the temperature for this person's room to this number over here. Let's call that X. And the reason for this is because now we can iterate, because the minions are sorted by their upper temperature preference. So these red lines over here, because it's sorted by these red lines over here, if a minion who comes afterwards has their lower temperature less than this mark over here, we know for a fact that these 2 minions are compatible with this temperature. This is an important point to understand, so I'll just explain it again. So we sort the minions by their upper temperatures, their preferred upper temperatures. And then what we do is for our first minion, pretend this guy doesn't exist. He's not a good example. We choose the first minion's upper temperature. So we choose this point, let's call it X. And the reason is now because we can iterate through the rest of our minions. And we know that if that minion's lower bound, so if their lower temperature is less than X, they can be in the same room. And we know that for a fact because we have sorted the minions by their upper temperature. We know that this upper temperature has to be greater than or equal to this X over here. Does that make sense? You should try to code this and the solution to this problem and play around with it for a bit to understand it better. But that's the solution for this problem, and I'll continue demonstrating. So let's say we had a minion. Let's say we had a minion whose temperature range was like this, and one that was like that. Yeah, that's good. So in this case, you can see that this guy's upper temperature, if this guy's the first minion in our list, I'm just going to write this out I'm going to give each of these a number because they're sorted by their upper temperature. So this has the lowest upper temperature, then this one is tied, this one is in the middle, and this one's farthest out. So you can see over here that this guy's lower temperature is less than X. And we know that these two guys are compatible at temperature X because we know that this guy's upper bound, minion two's upper bound, has to be greater than or equal to X. Because he was second in the list. Minion one was first in the list because his temperature, upper temperature was X. This guy was second in the list because his upper temperature is at the same value or after it. So the fact that this guy's lower temperature is less than X means he has the he's compatible with us. He can have the same X temperature and be fine with it. Now we look at minion 3. We see that we know for a fact his endpoint is after X. We don't really need to check that. All we have to check is whether the lower bound is less than or equal to X. And it is, it's over here. So we know minion 3 is fine. And the same way we know minion 4 is fine because his lower bound is before X. But then we come to minions 5 and 6 over here. So with minion 5, we know for a fact, once again, that his upper bound is outside of X. So in order for him to be compatible with minion 1, his lower bound has to be less than or equal to X. And you can see over here that the lower bound is not less than or equal to X. So that means we would have to increase our number of rooms by 1. So now we need 2 rooms, 1 room for this guy over here. And we update our X over to this value over here. And this technique is called sweep line. You guys can search it up and read more about it. But that's the solution for the minions problem. Are there any questions? I can show my code that may help. So basically we have our minions over here. And once again, PII, it means it's a pair of ints because each minion has a lower and upper temperature. You read that in. We sort our minions and we sort them by the upper temperature. So that's what this function does over here. It's to sort 2 minions. It looks at 2 minions and compares them. And we want to put the minion with the lower upper temperature first, and then the guy with the higher upper temperature last. So that's what this does. We sort it. We know for a fact we're going to have to need at least 1 room. So we just set our rooms variable equal to 1. And then num is our upper bound. So once again, I could replace num with upper bound to make it easier for you guys to understand. And our upper bound again starts at the upper bound of the first minion. So this guy over here. Phi stands for the lower temperature of minion I, and SE equals upper temperature of minion I. So now what we do is we go through our minions list and we check if this minion over here, so like minion 2, if minion 2 has a temperature that is a lower temperature that is greater than our upper bound. So for example, phi has a lower temperature greater than X. We increase our count by 1, rooms plus plus. And we also set our upper bound to that new minion's upper bound. So this would be the new X. And that's the solution for this problem.
Could I also just do this with strings? Like read in the input as strings and then sort them? And then go backwards, like traverse backwards through it.
Yeah, I think sorting by strings would work, but it isn't optimal. Yeah, sorting by strings would work if we had a string that looked like string S equals upper temperature and then space lower temp. I think that would work if you sorted it like that. But strings are generally slower. If you're doing it in Java, then yes, I can see why you'd want to do that. But you can also create a pair class. I think strings would work. And then you would have to use like string.split to remove the spaces. And then you could get your lower temperature and upper temperature. That's a good question. Yeah, and n isn't too large, so you don't have to worry about the string being slow. Yeah, and then so that we covered the first 4 problems. I don't want the meeting to go on for too long. So some of the other problems, this one used dynamic programming. That's another topic you guys can search up if you're interested. Dynamic programming. Feast for cats. That was a graph theory problem. It used minimum spanning tree, and you could have. This is also a pretty interesting problem, so you can check that out. Arachnophobia had a binary search and shortest path. I didn't do kaleidoscope or Gwen's gift. And then NVWLS was also dynamic programming. And for good problem practice, I recommend checking out the list of problems on Google Classroom. I put 2 new problems on there, and they also have video explanations and code solutions, so you guys can follow along and learn from that. Are there any questions about the problems, or do you want me to go over a specific one? Okay, cool. So next week, Kanishk and Madhu will be going over custom sorting. So like for the minions problem, if you're using Java, then if you didn't use a string, then you would have to create your own pair class in Java. So Madhu and Kanishk will be going over how to create your own classes and then how to sort them with your own custom sort function and comparator. So that'll be next week's meeting. And yeah, thank you for coming to today's meeting. If you have any questions, you can stay behind. Otherwise, you're free to go. Bye.